Hello, welcome to my talk on steady incompressible potential flow, the streamline path-line equations, and the streamlines and path-lines. As we all know well, in the steady flow, the streamlines and path-lines would be same. But why is this? I will use mathematical method to show why in the steady flow the streamline and path-line would be coincident. Therefore, in this talk, I will make an introduction on the streamline equation for the velocity field and the path-line equation for the flow field. Then I will use the example a steady flow past the cylinder to show the streamline equation and its solution, and the path-line equation and the solutions. Then we can see why the streamlines and the path-lines are coincident in the steady flows. As we all know, a streamline is an instant line on which the fluid velocity vectors are tangent to it everywhere. So we can imagine a number of small bright particles in the fluid, and we photograph their motion with a short exposure. This is actually the way PIV, particle image velocimetry, in measuring the flow velocity, such as the velocity vectors shown in this plot. And this instant velocity vectors given at the instant time t equaling to t0. And if the flow is steady, then the velocity vector would be time independent. That means whenever you take the photograph, you will see the velocity vector are all the same in time. And in an unsteady flow, the velocity vector would change with the time. Here, from the velocity vector, we can draw the streamlines. See the red dashed lines here. And obviously, we can see the velocity vectors are tangent to the streamlines everywhere. As we have already shown, the streamline equation would be given as this. So dx, dy, and dz are the increment of the position along the x-axis, y-axis, and z-axis. And correspondingly, the velocity component u, v, w are the velocity component along x-axis, y-axis, and z-axis. And the velocity component would be given at the time instant t0, but it would be dependent on the spatial variables x, y, and z. Therefore, streamlines are served at an instant time t0, and at different time the streamlines might be different depending on whether the flow is steady or unsteady. A path-line is a trajectory of the fluid particle moving in time in the fluid, which would be served in the Lagrangian approach. So we can imagine if we focus on a particular bright particle and photograph with a long expose to see where the particle moving around. The path-line equations are given mathematically for the flow field as the differentiation of the position with regard to time. dx over dt is the fluid velocity component u, and the dy over dt is the velocity component v, and dz over dt is the velocity component w. And we can see here the velocity component would be spatial dependent and time dependent, depending whether the flow is steady or unsteady. In the unsteady flows, the velocity component would be both spatial and time dependent. In here, we look at the different form for the Parsonage equation. Based on the definition of the Parsonage equation, we can write the equation in different form given as this. So dx over u is dt, and dy over v is dt, and dz over w is dt. So equaling all this equation, we have the different form of the Parsonage equation given as this. This is very similar in the form as the streamline function. The difference would be in the Parsonage equation, the velocity component, see here, would be spatial and time dependent. And the Parsonage itself is the time history of the fluid particle traveling in the flow field. Streamline equation, the velocity components are given at an instant of the time. Thus, the streamline is an instant curve. Next, I will use an example to show how we can build the streamline and the Parsonage equation and how we can solve that. So the example is the uniform flow with the velocity u0 past the cylinder of radius of r. In this talk, we will study the problem analytically. Thus, we assume the flow is a potential flow, and the flow velocity is not very high, hence it is an incompressible flow, and the flow is a steady flow. For such a potential flow, the uniform flow past a cylinder, there is an analytic solution. The details of the solution can be found in my talk on simple potential flows. Here, the solution is given for the velocity components in polar coordinates as ur and u theta. ur is the radial velocity, and u theta is tangential velocity. And if we draw the velocity vector of the uniform flow past the cylinder, we can see the velocity vectors as this. And this is the transform of the polar coordinate and the Cartesian coordinate x, y with r and theta. And based on the vectors of velocity, we can draw the streamline. So we have the drawing like this. And we can see everywhere the velocity vectors are tangent to the streamline everywhere in the fluid. For such a flow field, the streamline can be solved from the stream function given as this at the time instant t equaling to 0, given as this. And we can substitute the velocity component into the streamline equation. We have the equation as this. And we will show how we can solve this streamline equation. We can make some mathematical manipulation to this equation. We have the equation as this. We move r to the left-hand side of the equation and theta on the right-hand side of the equation. So we can also separate this term. We have the expression as this. And now we can see this integrable as this. So the solution would be given as this. This is the streamline equation, and C is the integral constant. And we can use C to define the different streamline. For different C, we have different streamline. Thus, the different C would correspond to different streamline. See this plot, and for different streamline, we have different C. Now we have a look at the path line and the path line equation. As we have mentioned before, the fluid path line would be solved from the path line equation in Lagrangian approach given as this. So the partial differentiation of dr with regard to dt is ur. So we have the expression for ur as this, and r d theta over dt is u theta. So it is given as this. So we have the velocity component ur and theta before. And we can see the velocity components are time independent because this is a steady flow. Superficially, these equations are quite simple because there's no time in the velocity component. However, the velocity components are the functions of r and theta. Therefore, the integration of this equation is very difficult, if it is not impossible. However, since our purpose is to find the trajectory of the fluid particle, thus for such a steady flow, it is possible for us to remove the time factor in the equation. We can do this by dividing the first equation with the second equation. So we have the expression as this. So this is the different form of the path line equation. Can be written as this. And if we compare this equation to the streamline equation, we can see they are exactly the same, since in the steady flow, ur and u theta are only spatial dependent. They are time independent. And for such an equation, we have shown in solving the streamline equation, this equation is solvable. Now we can see in the steady flows, the path line would have the same equation as that of streamline. This means in the steady flows, the path lines would coincide with the streamline, and the solution of the path line equation would be same as that of the stream function given as this. So we can see the path line and the streamline are constant for the steady flow of a uniform flow past the cylinder. So the black lines are the streamline and the path line. So this is the proof in the steady flow, the path lines and the streamlines are constant.